I am about to bestow upon you the supreme knowledge of creating any material known to man and then some. And by the end of this masterclass, not only you will know everything you need to know about procedural and texture-based PBR material design, but I will have forever changed your mindset about node-based visual scripting. So if tomorrow you get deployed into any other software like Unreal Engine, Touch Designer, or Adobe Substance, you'll be like, bro, I got this. Okay, let's go. So the very first thing that we'll do is to make sure that we have the node Wrangler enabled so we can work like actual pros. To do that, we'll go to Edit, Preferences, and in Preferences, we'll find the Add-ons tab and scroll down and make sure that the node Wrangler is enabled, like here. So this is an add-on that ships with Blender, and I believe that in the later versions, like 4.4, it is enabled by default. And basically this allows us to use certain shortcuts and other extra functionalities. And this is probably a very good time to highlight that shortcuts are not secondary methods. They are not an alternative way to do things. They are the main way. So there are a lot of commands that are accessible only via the hotkeys. And this is actually true for any software in any industry. It's not just Blender. Not knowing your shortcuts is the first sign of being a rookie. Now, you don't need to know absolutely every single one, but the point is that pros need to move quickly and stay focused on their task. They don't need to go and find options in a menu. So it's like playing the piano. Your hands need to know the keys so you can focus on what you're playing. Okay, with that being said, as we are about to start, let me give you a read of this video. So in this video, we will go in great detail into both procedural PBR materials and also into texture-based PBR materials. We will see the pros and cons of each. Now, because we will go in such great detail on so many materials, this will not be a step-by-step video. So this is not about you learning and following me as I make this node and then I hook it up with this other node. That's not it. This is the video that comes before. This is the video where you absorb the most important concepts. I'm gonna highlight and stress so many times the most important concepts throughout this video. That is what you need to take home from this lecture. And then this lecture will be followed by other masterclasses on equally important topics like lighting and composition. And then when we have dived in depth on all the major topics that we need to dive into, then we will have one big step-by-step walkthrough where together we will put all of those things that we're now seeing in great depth into action. Now, one thing that I wanted to show you, since we will be working with textures, and so you know it now and forevermore, is that if you go to File, there is a tab here called External Data. And if you automatically pack resources, like I just did right now, Blender is going to pack into your Blender file, that is the project file you're working in, all the textures and all the assets that it needs to have referenced that are usually external to the file. So for example, when you have an HDRI or when you have texture images that are linked and referenced to your file, if you move those files, if you change the directory, if you rename those files, or if the project moves to another computer, then you will have a big pink warning everywhere. Things will go missing. And so to avoid that, you can pack the resources with the Blender file. And now everything that is within the file, it's embedded and it is with it wherever it goes. Mark this down because that is super important when you are working with referenced material and resources and you need to move your files across computers. This is the way to do it. Okay, with that being said, here we have an object that I created that has some complex shapes set up so that we can see how materials behave. And assigned to it, we have the default material, which if we bring up the shader editor, we'll see is the usual basic principled BSDF, which I remind you, it stands for bidirectional scattering distribution function. So let's review for a second the basics as we have covered them previously in video 16. So when you create an object, any object like a primitive, it comes in and it already has a material assigned to it that will read material, and it is the default one, which is this one. You can create new materials and sort of attach them to the same object by clicking on plus, and then you will have to click on new. Or if you have already previously created another material and you want to assign it to this object, you can go over here, and as you can see, we have plenty of materials in this scene already. But if you wanted to create a new one, you would click new, and then you would have material 001, and then you can assign it. And so also reminder, if you go into edit mode, for example, I could click L and have this linked surface selected, and then assign this material 001. And if this was of a different color, it would become apparent that within the same object, we now have two materials, and this one is the second one. And so this part of the mesh has been assigned this material. And while we're at it, we can review the basic properties of materials. So what we have looked so far is the basic color, which can be changed easily from this menu. The metallic property, which reminder should always be either 0 or 1. And the roughness, which basically determines if the object is mirror-like, super smooth, super polished, or if it is very rough and rugged and light interacts in a way that reflections get scattered in a way that doesn't make any sense to the eye anymore, and we are no longer seeing reflections. Then the IOR, which stands for Index of Refraction, we will see it in much more depth in a few minutes, but as a reminder, it is a value that tells us in many ways how an object is interacting with light. So, for example, right now that we have what would be a totally black and rough material, you can still see that it is pretty much interacting with light. However, if this IOR would be dropped to 1, it would become an absolute black, like a black hole that sucks in the light and lets nothing escape. And then we had seen the alpha, which basically determines the transparency or opacity of a material. And then the normal, which basically is something that we can use to sort of add more detail to the geometry visually. So without having to build extra geometry, we can provide extra informations for the software to render something that looks more realistic. Now I'm going to bring myself in object mode and I'm going to press on minus to remove that material since we don't need it anymore. And now we will actually start with the serious stuff. Okay, so here we have the first material that is a simple copper metal. Now assigned to it, rather than the principal BSDF, we have a metallic BSDF, which is one of the newer nodes that have been added to Blender. And what this does is that it allows us to render very precisely specific metals as they are in real life. So if you remember, PBR stands for physically based rendering. So all of this, as we have covered in video 16, is based on actual real-world physics. And this would probably be an excellent time to remind you that right now we are in rendered mode over here. And also we are using cycles with GPU compute enabled. So cycles is the render engine. The other render engine that exists in Blender that you can use is Eevee. The fundamental difference is that cycles is geared toward realism, and the way the render will be calculated will be through ray tracing, which means it's actually going to calculate how the light behaves with the material to give you sort of the most physically accurate result possible. We will cover render engines in much more depth in another class, but this is the only thing that you need to know at the moment, that we should be in cycles, and that cycles, at the cost of being more computationally heavy, creates more realistic results. Whereas Eevee, which is, for example, the render engine that I used in the previous video, is geared more towards stylized results. And then we want to make sure that we have GPU compute enabled so that we are using our graphic processing unit, which is the part of your computer that is tasked with handling the heavy work that we are doing here. Now, back to the material. As I was saying, we have a metallic BSDF, which is one of the latest additions to Blender. The fundamental difference is that it has two modes, let's call them like that. Now the default will come in with the F82 tint, which is fundamentally what you're seeing over here. This metallic slot, this abstraction that creates a metal over here, is fundamentally what the F82 tint does. And so what I have here instead is the physical conductor, which is what is of interest to us from the metallic BSDF, which is an alternative, more accurate way of creating metals. This is great if you need to have accurate scientific rendering, for example, or to make sure that you are rendering a product and the simulation is as realistic and accurate as possible. And the way this works is basically that you have three values for the index of refraction of the separate channels, and the same goes for the extinction. So these are RGB and RGB values. Okay, this is a vector. So like we have said in video 16, which was a major lecture, we said that light can behave like a wave, and it is part of the electromagnetic spectrum, and that there is a portion of that spectrum which is what we understand as visible light, as visible colors, and that of that portion what we perceive are three main peaks that are the red, green, and blue peaks. And that is why all of our display technology is based on those frequencies, and why the display that you are looking at right now, it's actually made of teeny tiny LEDs that are red, green, and blue. And these values that you interact with basically command the brightness of those LED values, right? So in the real world, metals have at the atomic structures electrons that are delocalized. They can move very freely. That is why they are good conductors of electricity, but that is also why they are so shiny, because the electrons that are delocalized can move freely, and so they interact a lot with the photons of light that comes and hits them, okay? And so what this handle does is it abstracts for the artist, for the user, this interaction, right, of delocalized electrons in the material. And with the metallic BSDF, through the physical conductor option, we have the ability to put in exact numbers that represent how exact materials behave. And so here we have the values for copper. Now, of course, you will not learn by memory all of these values unless you're doing, I don't know, like a PhD in metallurgy. And so what you can do is find charts like this one at physicallybased.info that provide you with the exact values of several materials, which is the one, for example, over here with chromium that I used in our next material. And so here we are to our next material, which is chrome. So recently we 3D modeled a coffee maker that had copper and chrome materials. And as you can see, the metallic, the SDF, has also a roughness value. And just like other nodes, the roughness indicates the quality of the surface, right? If it's very polished, very smooth, or if it is very rugged. And so here we can see that because this is very close to a mirror surface, we are seeing a reflection of this object that we have here. Now, since this is the most mirror-like material that we have here, this is a great moment to point out a pro tip. So, like I have told you many times, you should stay away from the absolutes. So, no material is in reality actually ever to a zero value, a perfect value. Nothing is this smooth. All materials that you set up, if you're aiming for something that looks realistic, should have some roughness, okay? Just a little bit at least. But I'm gonna set it for just a second to 0 to have an improbably perfect mirror, just to point out another thing that here we are in the same editor, the shader editor, but for the world. And we have our setup that we reviewed in the HDRI video. And right here, I have that part of the node 3 that is creating this blurred effect. Now, if you remember, I told you if you bring this to 0, it would be like not having at all any blur in the environment in the HDRI, right? And I told you the reason why you want to have this more advanced setup and have some blur is because sometimes the camera is not enough. So objects that are in the distance, right, should be a little bit out of focus, right? However, if you have a reflection like this one, one of the best ways to actually create something that is accurate is to actually make the landscape a little bit blurred. Okay, so now that this is out of focus, the reflection of this mirror-like material is actually accurate, so that the distant environment that is very far away is out of focus, and the object that is right here and reflecting into it is actually pretty sharp. And then because we want things to look really, really well, we are also introducing a little bit of roughness over here. And now this looks very good. So moving forward, we have here another metal that is using the physical conductor mode. So we have here a physically accurate aluminum metal that, as you can see, has a higher roughness, and therefore it interacts differently with light. And so whilst it still is reflecting the same environment, the reflection that comes back to our eyes, it's much more scattered, and this is why it looks like this, because less of the image finds its way back to us, and so our brain interprets this as less of a mirror, okay? And now we have to introduce something else, which is the anisotropy. So the anisotropy, let's break it down. First of all, the isotropy, right? Iso means equal or like same. And tropos, which is the root of tropy, means turn or direction, right? So isotropy means that the light hits the object and then gets scattered back in sort of the same direction. And then an, the prefix an, is a negation, so not in the same direction. And so when we turn this on, like we did over here, what we have is that the light from the light source hits the object, but then when it hits the object, it doesn't get scattered back in the same direction in equal ways. So basically, the reflection and absorption properties of the object get changed based on the angle at which it's viewed. The reflection is changed. And so this sort of represents an abstraction of what in real life is a behavior caused by very fine scratches on the material, or for example, brushed metal that has been worked in a certain way. And in fact, what we have as the next material is brushed aluminium. So we have the same exact aluminium that is using anisotropy to create a realistic effect for machined metal that has this clear machined pattern. And here we step into our first slightly more complex procedural setup. So procedural setups are visual scripting. They are node-based visual coding. We are by all means coding the material, except that rather than writing text in traditional code, we are linking nodes, which are packets of code that has been bundled into a friendly user interface. So rather than having to type things every time, you can just summon a node and then link it. And then this allows us to create very complex trees very rapidly, as opposed to having to hard code them, for example. So let's take a look. What do we have here? First of all, nodes, they go from left to right. This is a general rule across most softwares, much like code when it's written goes from the top to the bottom. The execution is from left to right, and that is why you want to keep your nodes in a sort of like linear fashion and not stack them one upon the other like this, unless it absolutely makes sense for the specific case. I have done it here and there in this project when it made sense, but as a general rule, this should go like this, left to right. And so if we unplug this by left clicking on it and letting it go, what we have here is fundamentally the same material, with the only difference that the anisotropy here is slightly curved down to 0.5. And what I have here, first of all, is a tangent node. So you bring up nodes by pressing Shift A, search, and then you type what you're looking for. Or you can press Shift A, and here you have everything that is accessible to you. And as you can see that there is a lot of stuff, but over time you get to know this by heart. And so the best way to go about it is to actually search the first few letters. And so here it is, tangent. Now this tangent allows me, when plugged into the tangent socket, to change the tangent of the object, which is how this anisotropy is created. So if we look at the manual, technically this slider is changing whether the incidence is along the tangent or perpendicular to the tangent. If this doesn't make sense to you, you can by all means just plug it and play with it and see what looks real to you. As you remember, many times I have said that a big aspect of doing this kind of work is also, does it feel right? Because things might be accurate scientifically, but not necessarily feel right. And that is why you exist, to make them feel right. Now, the next part, which is creating the whole magic, is this part, which is nothing but creating a circular pattern. So because we have enabled the node Wrangler at the beginning, I can press Shift and Control and then left click on this node. And what this will do is that it will pick the node that I've clicked and will link it directly to the material output, which will create for me a sort of immediate preview of what is happening so far in the tree. So this is the node tree so far. It started here, and by the time these nodes went through and arrived at this point, this was the result that was coming out of this color output. And so as you can see, we have fundamentally a noise that has been made into concentrical circles. And this is where we stop for a second and I reveal to you the secrets of the universe. So the one thing that you need to understand about reality is that everything is noise. I'll say that again. Everything is noise. It's all noise. So the moment you understand that everything is noise, it's like when Neo in The Matrix realizes that he doesn't even need to dodge bullets. That's it. Everything is noise. All about your reality, your perception of reality is a construct that is created by your brain. And all that you are perceiving is noise. So let me demonstrate this to you. I will now play for you a noise. And most likely you can't make any sense out of it. But what you need to understand is that from reality, through your senses, all sorts of noisy signals come through. May they be light or sound, may they be light in the visible spectrum, or, for example, EM radiation that comes in as infrared and you perceive as heat. All of this is coming in as noise patterns, and all that your brain does is that it finds repetition in those patterns and uses prior expectations to make sense of them. So I'm gonna play for you again the same weird sound, okay? And now, to demonstrate that everything is absolutely just noise, I'm gonna tell you, I think Brexit is a really terrible idea. And now that I play the sound again, you can hear words in it, right? So that is a demonstration that prior expectations and context is what the brain uses to construct your reality based on noise that is coming to it through your senses. So as a 3D artist, the one thing you need to understand is that if everything is noise and the perception of reality is based on a biased construct that can be biased in any direction based on little suggestions, then with noise you can create everything. And that is what we're going to do today, that using noise, simple noise, we are going to create all the materials that you can possibly imagine. Let's go back here. Take a look at this one, right? This is just noise. This is fundamentally like white noise, the equivalent of like a radio going static. And all that we're doing is that we are taking this noise that is very hard to see because the render engine tries to resolve it. But as I move, you can probably see it better. We turn all this noise and we sort of like stir it so that it becomes moved in this concentric pattern. And then this is a color ramp that is taking this noise and is accentuating the contrast between the white and the black. And we do so by sliding these two handles over here, which by default in a color ramp come in like this so that you have a smooth gradient. And I'm gonna plug it in here and demonstrate. So we have this concentrical pattern coming in, and if I bring this up, I am going to accentuate the darkness, whereas if I bring this down, I'm going to accentuate the lightness. And so we are fundamentally compressing the range that is available, and by compressing it to this very small portion, the contrast gets bumped up. And then finally we plug this noise, this black and white, into the material BSDF. Now, if you remember, if you watched video 16, at one point I said that everything, the one thing that you need to understand about PBR materials is that all of these are values, and most of these are between 0 and 1. And even those that are not, they are within a range that can be mapped to 0 and 1. Okay, so it's all about black and white and the gradient in between. It's all about 0 and 1. And even with colors and normals, which are vectors, which are made of 3 channels, these individual channels, if taken individually, are grayscale. They go from 0 to 1. Okay, so even when we bundle up these things into vectors of 3 rather than vector of 1, we still are dealing with these values. Now, the moment you understand this, and the moment you understand everything is noise, you can do all sorts of things, because what a slider allows you to do is to change the value in a homogeneous way, uniformly across the whole object. But we have sockets where we can plug things in, so that now we can say where it is black, it's 0, and where it is 1, it's white. And now when I plug it in, rather than having a uniform roughness that is 0.5 everywhere, I now have something more sophisticated that maps one-on-one this value, as you can see. And we're just saying where it is black, it's gonna be smoother and more shiny, and where it is white, it's gonna be more rough and less shiny. And that's it. That's the key to any material known to man. And now we'll see how to apply that. But this is fundamentally the inner truth of your universe, of how you perceive reality. It's all about noise. Now, like I said at the beginning, this metallic BSDF, when switched to F82 tint, is nothing but a principled shader using the metallic. And as you can see here, it's pretty much the same setup. The same things are happening. What the principled BSDF is actually is simply a bundle that has in it all the main shaders that you might need, right? So for example, if I go and search for shaders, we have a ton of shaders, a diffuse, a glass, a glossy, and so on, right? So the principle sort of bundles them together in one node from where you can tweak things and achieve fundamentally any material. And once again, we are using the same process to create this noise, making it concentrical and then passing it to the roughness, with the advantage that right here I am picking colors with the F82 tint style. This is more of a eyeballing thing to create this kind of rose gold brushed metal. And once again, this tangent, if you still had troubles understanding it, is fundamentally changing the axis for the tangent and affecting how light interacts with it. So as you can see that if I toggle it, it changes how the light finds its way back to our eyes, changing fundamentally the highlight, this bling effect. Okay, and now we finally get into the power of procedural materials. In the principled BSDF, what we are passing as noise here is fundamentally some visual information. Now, this visual information could be constructed through a series of nodes procedurally by, for example, creating noise, right? So these are mathematical operations. Or we could pass in textures, which are images as in, traditional PNG or JPEG images that have a size, and you upload them and you pass them in, much like we have done with the HDRI. Now, the power of procedural materials as opposed to textures is that textures as images have a resolution. They have pixels, they have a size, and once you go to their maximum resolution, right, you start to see the pixels. Whereas, because this is procedurally created through mathematics, it's the equivalent of a vector-based image, which doesn't rely on pixels, and so you can zoom in as much as you want, and you will always have more details if you wanted to. Another aspect of procedural materials is that all of this is a non-destructive workflow. So it means that the material is live. You can change values even at the beginning of the node tree, and then the change will propagate all the way to the final result. So for example, I could change this, which was the value affecting the noise for the concentrical pattern, and make it slightly bigger, and that will cause the material to update. And although it's very difficult to see, let me put something very small. This is affecting the pattern that we're using to create this brushed effect. And finally, the idea of working with procedural materials is that you start to create a large amount of masks that are this black and white things, and then you use them to let some information pass through and some other information not passed through a gate. Okay, so what have I just said? Let me zoom out, and now you probably start to get scared, like, oh my god, what's all this stuff? And now we're gonna make sense of it. So what we have here is the same setup that we had here. So this setup is creating our brushed metal, okay? And like we said, once again, this is creating the noise and making it turn into circles. This is strengthening the contrast, and this is giving it color, and this is outputting the final result. If once again I press Ctrl Shift click on this one, we are now previewing the result at this point of the node 3, right? And so we have the same exact results, same exact setup. Here the color is slightly warmer because this is meant to be copper, although this is not with the physical conductor but with the F82 method, right? Now just below, what we have is a similar setup where we have another principled BSDF, okay? And so by now we know that principled BSDF is the material, right, that gets created. And in this case, what we have is a noise texture, this one, that is getting passed through a color ramp. And in this case, this color ramp has several handles and it's colored. And so all that this is doing is creating a palette of colors for us, and it is assigning it to this noise. So as you can see, it maps 1 to 1 because this is the same noise that now is just getting colored. Then this color ramp is going into a hue, saturation, and value, which is a node that allows us to control the hue, saturation, and value, of course, of the color that is passing through it, which allows us to change things like the hue and saturation fairly easily, right? This is why we put it in, to have a much finer control. And eventually this thing reaches the principled BSDF and creates the color that we see in the outputted material, right? Now from this noise, I am sending the result also in a color ramp. And this color ramp, which as you can notice has a much lower range, at least to your eyes, is going from 0.5 in value to 0.8. And although it's harder to see it, it is still the same noise that is simply basically being grayscaled and shifted towards the white. Why are we doing this? Because we want to have the same noise, okay, but ranging from 0.5 to 0.8 so that we can plug it into the roughness. And again, rather than having the whole object at 0.5, we can have it so that some of it is at 0.5 and some of it is at 0.8 and some of it is in between. And then the last thing that I'm doing is taking the original noise and sending it to a bump. Now, a bump node is fundamentally taking a black and white image or noise or procedural information, and it is turning it into a normal vector. So what we're seeing over here are the RGB channels that are used to convey the XYZ information that are used in the normal. And here we have a brilliant example of how normals are used to convey extra information, right? So we are making this material look like it has all this very rugged, thick patina surface that has not been 3D modeled in there. And if I turn this up, I can control it and bring it to an extreme, of course. And if this was 0, we would not have any effect at all. And so I'm going to leave it to a 0.25, which works for me. This feels right. And so to recap, what do we have here? We have this metal and this, which represent the verdigris. This is a patina. This is when metal oxidates over time. It is exposed to the weather and the elements and eventually forms a patina on top of it. Just like rust for iron, copper forms this verdigris patina that leans towards this beautiful robin egg blue color. And what we're going to do here in our next node in the tree, we are mixing them. However, if we were to just mix them, 50 and 50, it would be weird. So what we're doing here is that in the factor, we are passing a mask. And now we'll see how that mask has been created in a moment, but this is the mask. And once again, it's all noise and it's all black and white. White is 1, black is 0. And so if we look at this, what do we have here? 3 pieces of information. The mask, the shader A, which is 0, and the shader B, which is 1. So this is telling it, this mix shader, take whatever is coming through this part, and wherever it's black, let it pass through, and wherever it's white, let the other shader pass through. And look at that. This is what happens. That this material that is coming through here, where it is black, is passing through. And where it is white, is letting the other one pass through. And now we have a mask that is starting to represent a material that has started to decay and etch and oxidize. Now, as materials decay over time, right, they decay in very specific ways. So, for example, they are much more prone to losing their original color or the original quality of their surface along the edges. And so the way that you figure out those edges is by using several methods like we have here. One of which is ambient occlusion, right? So ambient occlusion is when you have a situation like this one, where you have some sort of like corners because multiple surfaces are emitting and the light is not really finding its way into those crevices. And that is where ambient occlusion comes into play. That's simply saying that these areas are darker because there is less light reaching that point. And so by taking this node and passing it through the usual color ramp and then cranking up the compression, we obtain this mask. And then we use it or here in a chain of mixes to let pass through once again the result coming from the previous node and letting pass through the other one. Okay. Let me go through them actually in order so it makes absolute sense. We have these two materials, they go in here, and based on this mask, we achieve this result, copper passing through here and verdigris passing through here. Then this result is passed through the B result of this one. So we know that everything that is going to be white coming from this mask is where the previous result of this one is passing through, whereas where everything is black in the first result, everything is going to be like this, which sort of help build up a little bit more of the sort of patina effect. And this other mask is basically using the geometry node with pointiness to sort of determine changes in the surface and create this mask. And this other method is using bevels and noise to sort of create these other masks that eventually lead to this result. And so what you have to understand of this part is not to commit to memory exactly how this is set up, but more that you can get some sort of information, get some sort of noise, and then through the color ramp, always through the color ramp, you end up creating this black and white logic, this black and white mask that lets things pass through a gate. And so by the time we get here, we have successfully stocked up all of these masks and have achieved this result by a multiplicity of operations that lets this pass through in certain ways and this pass through in other areas. And of course, just like code, this is not the only way to go about it. For example, rather than doing 3 passes where all of these masks are brought in at 3 separate stages, what we could have had is have a moment here where we summed the black and white areas of these separate masks and created one mask that plugged into one mix shader and outputted the result. This is simply how it came out in the process of building it. So it could definitely use some further optimization to reduce the number of nodes. And then what's happening over here is that materials don't just erode at the edges, but get scratched all over. And so once again, same exact logic. What we have over here are masks that are using another type of noise called Voronoi and using color ramps to create the noise texture that we need over here, right? So what do we have here? There's a texture coordinate and a mapping that is telling this Voronoi noise how to sort of get displayed over the object, okay? We have a noise texture that as is doesn't make any sense, but when plugged into the location, fundamentally brings about this kind of distortion. So the noise texture, when plugged into the location, helps distort this noise further. So we have a sort of inception moment where there is a noise distorting a noise, right? And then the result is passed through a color ramp to compress it. And as you can see, you know, it's always the same. And what we have here is the exact same noise, but with slightly different values. So you can see that they're not random. They're following, if you look over here, the same distortion. And then we're using this operation to sort of like curb this down to this one because we only need so many scratches. And then a final refinement before we pass it as this mask. And then this ends up being the final result where we have this copper that has been scratched over time. And where it has been scratched, it has started to erode and oxidate and turn into this beautiful verdigris patina. Nice. So, for those of you that are seeing this for the first time, it might seem overwhelming, but like all things in Blender, it's super modular. You only need to understand the essential parts. We have a material happening over here. We have a second material happening over here, and we are creating a bunch of masks that are black and white with noises, and then using logic gates to pass through and alternate which of these two materials get shown. And because of the way those masks are, you know, looking, we end up with this scratched, eroded surface. So let's take a look at this one, which is the next one. And if you look at it, it's fundamentally the same setup. What have I done differently? Well, simply, I have created this base material, which is the equivalent of this base material, and I have set up a bump that is stronger, and so it is creating this more rugged surface that looks like cast iron as opposed to machined brushed copper. And then, just like we had a separate material for the patina, we have a separate material for the rust. So in iron, the rust tends towards red, at least in normal conditions. And then we have the same exact modules that we used over here, just copied and pasted with the same exact logic to create this effect. And so here you can see that the power of the procedural approach is that not only it allows you to create infinite detail and control absolutely everything about all aspects of the material, like where is it scratched and where is it not scratched and so on, but it also affords you, once you create an efficient node, to recycle the same nodes and use them over and over and over. And because all its noise, you can use the same nodes to do all sorts of materials. And so the next one that we have is molten iron and lava, right? So if we dump this into a forge, what we have is the same exact setup with just a few minor adjustments. Like, for example, I created this emission shader. An emission shader is nothing but a traditional principled BSDF that, on top of having a base color, has also the same information plugged into the emission color, which fundamentally tells it that this is emitting light of its own, right? So usually materials receive light from a light source, but when they have an emission set to it, they also emit it. And then, once again, because everything is noise, with the same exact formula, we can create this effect that starts to look like this metal has been melted and is actually in the process of melting and getting reforged into something else. And once again, to go back to the Matrix reference, why is this working? Because all of your reality, all of your perception is nothing but a guided hallucination. You are being hinted towards results, outcomes. And so because I am hinting at you that this has this palette, and because you have had previous experiences, you look at this and you see molten iron and lava. Not only that, but we as creative people, we can bend the rules. And so I could change this significantly. And now we have maybe some kryptonite glowing material, or if we go the other way, we can have some sort of weird plasma material. And so not only you're able to create any material known to man that actually exists in reality, but also materials that do not exist in this world, but can exist in our imagination. Moving on, what do we have here? We have Damascus steel. So what's Damascus steel in real life? It is metal that has been folded over and over and over many thousands of times, and because of also the specific impurities that you have in the metal, it starts to show these patterns. And guess what? Those patterns, those beautiful, noisy patterns, are nothing more but the same usual setup, which here I have simplified because we have less things happening, but it is more of the same. So let's take a look at it. We have a noise that is being generated like this. Then another noise is further distorting it, right? So this is distorting it further. And then we are compressing it until we create our black and white situation that we are using to do what? We are using it to, first of all, mix it with the color to create our base color that goes in here. We are then using the same exact information to create this other map, which goes into the roughness. And we are using this material to go into the bump and create this information for the normal. And so what we have here, using the same exact operations that you have seen used in all these other materials, we are somehow going from having brushed copper and rose gold to Damascus steel. And here we have another material, which is iridescent paint, like you would see on some very exotic hypercar, or maybe on some gadget that has this sort of like metal finish, which is quite popular. And what do we have here? Well, this by itself is a super simple material that you could have achieved very, very simply by simply creating a layer weight node, which is fundamentally creating a mask that is responsive to your point of view. And as you can see, if you look at here, you have a real-time mask that is white in some points and darker in some others. And you can change it as you go, right? Awesome. And what's happening after? Well, this map is being plugged into this to create this color effect. And this is nothing but the usual color ramp, which has been switched in color mode from RGB to HSL and from linear to near. So in this case, it's going from this color to this color, whereas if you were to put it as far, it would sort of do the opposite way around the hue spectrum and create a different effect. And now that you have it plugged into a BSDF that has been defined as metallic, you have this effect, but this is a very simple result. And because we know that nothing is this perfect, to make it look a little bit better, what we have here are additional pieces of information that creates this sort of patterns that really bring in those small details that make the difference between a very simple material that only just hints at what it is supposed to be versus one that has been really studied to be as realistic as possible. And while we're at it, just look at those beautiful reflections on the Damascus steel. That's just beautiful. Okay, so moving on. What we have here is our last metal material, which is by far the most complex I have created. And so this brings me to a new topic. When things get really, really complex, what we need to start to keep working in a manageable and professional way is to be very organized and label things so that at a glance we know what we're working with. And so here we have areas that have been separated, And these are fundamentally the same exact setup that we have in the previous materials, right? There is a paint color that is being created, okay? And there is a rust material that is being created. And then there is also an exposed metal that is being created. And through a series of logic gates and masks, we are getting to the final result, okay? Per se, it's pretty straightforward and not at all different from what we have seen before. But in terms of quantity, there is a lot of things that are happening. And so if we are working in a professional environment, if we are working in a studio, odds are that we're not working alone. We're working with other people. And if not that, I can promise you that in 2 weeks' time, I will not remember what the hell have I done over here. And so it is also a form of respect towards my future self to label things and organize things so that if in 2 weeks' time or a month or a year, I need to go back and change something because maybe I'm recycling this for another project, then I know what I need to touch and what I can leave as is. And so once again, other than labeling these things in groups, which you can do by pressing Shift-A, search, frame, and this is, by the way, a common best practice across all softwares that use visual scripting to create frames that can label things and groups so that everything makes sense. So what I've done here, I have labeled all the things and we have the usual edgeware masks, right? The 3 main colors that we're using. The same exact setup that we previously used to create the final mask here has been duplicated and changed. And so I think this is yet another great example that same exact setup, same exact nodes, we change them a little bit and we go from here to here, right? Totally different result just because we tweaked some things along the way. And over here we have a sort of like final extra details layer that I've created. This is a very simple dust material that I have literally, picked, I think, the rust and duplicated it and changed it a little bit, okay? And then created the most simple of gradients as if this object, which has obviously been decaying for a good while, has been sealing up in the dust. And so at the bottom, I would have more dust and not too much at the top. And here I have this gradient, right? And, you could totally go the other way and go and try to be more realistic. So for example, if you really wanted to go for realism, probably you would have dust falling from the top due to gravity and then having occlusion zones where it doesn't have a direct falling line that are not dusty. You can spend, so much time on it. In the end, what matters is that it feels good, okay? This is by all means pretty much up to specs with a game asset, okay? What would happen in a production is that after the material has been, locked in, that we have decided that this is it for this asset, we would then go through a process called baking, which would sort of like freeze this setup in time. And so we can no longer change it, but the advantage is that then we move to a texture-based setup. So the baking produces textures. And although we can no longer edit the procedural parameters, what we have are textures which are much more efficient computing-wise, which is crucial when you are playing a video game, for example. And you wouldn't necessarily have near to infinite level of details like you have here. You could continue to go inside this surface and still find more details. In a texture, eventually you will reach the limit of its own resolution. Even on an 8K texture, you will reach the limit. And, sometimes that can actually help to bring things together. But at the same time, information is going to get lost. So again, procedural based and texture based are two different approaches, each with their pros and cons. And what we need to get out of this material is that, once again, through a series of logic gates and masks, we are able to produce every material in every condition across space and time, right? So this was originally a metal object with some paint on it, and eventually it got etched. The enamel paint etched, and then rust started to sink in. And because we are procedurally operating here, I could go into this node and change the paint to something else if I wanted to, for example, right? But I think I will leave it to a nice green, because green is the complementary color to the reddish tint of the rust, and so that creates a really nice chromatic contrast that really helps to sell this object. Next up, we have some wood, okay? And of course, you could create any kind of wood you want, from walnut to cherry wood. You are free to create anything that you want. It is totally possible. Here, I created only one because, time. And also because I think at this stage, I've driven my point across, which is that by using the same nodes, it's always noise textures. This is another kind of noise called wave that does nothing but creating noise pattern that is, like lines rather than looking like this. And what else? What do we have? The Voronoi, which I have not even used in this setup. So by using fundamentally three nodes, the noise texture, the wave texture, and the Voronoi texture, we have access to all the possible noises that we might need to create any material. And with the same exact process, we are now creating wood instead of metal. And so all there is to wood is that it is not metallic. The roughness tends towards higher levels, right? Because it's not as shiny. And we might have higher or lower bumps intensity in the normal, depending on whether this is the bark of a tree or a very polished, piece of wood that has been worked. And let's just briefly review it. What do we have? We have some noise that is creating this wave texture. So a wave texture can have several parameters. Here we are bringing in some distortion to create this jagged, veiny movements rather than absolutely straight lines. And then we are messing up a little bit with more noises to eventually create this map. Then we're sending this map into this other setup and also into this part of the tree, which contributes to the roughness and the color. Just like this part comes down over here and goes into the color and also the roughness, right? So let me say one more time, just to be clear. We are creating some noise here. And then we are mixing it with this noise over here, but at the same time, we are in part using this noise to further alter this one. And so in a way, it's like this noise gets mixed up over here with itself after having been changed a little bit over here. And down here we have this very simple sort of like striation pattern just to add in some extra little details, like little kind of like scratches along this axis. And all that is coming out of it are these two pieces of information, which are the color and this one that we are using both for the bump and the roughness, ending up with this wood that we can change in intensity of value, saturation, and hue, so it becomes pretty versatile. Okay, and so before we get into the very complex things, a small recap is that, again, all of reality, as far your construct of reality is concerned, is noise. It's all about signals that are coming through your body, and your mind is constructing reality out of it based on previous knowledge, okay? And so what you do as a professional artist is guide that biased, guide that noise with suggestions so that something looks like etched copper with patina, or fused metal, or etched metal paint, or wood, okay? This is the fundamental key to PBR materials, that all of this is about black and white noise. And this is true, like I was saying at the very beginning, for any other software that is based on visual scripting. The one thing you need to understand to master it all is that it's all signals. It's all 0 and 1. It's all right there, right? This could be sound coming in, and I could map that sound between 0 and 1, and then I would have roughness or normal maps that are reactive to the sound. This could also be a value that represents the distance of a light to my object, and as it gets closer, it becomes smoother for some reason, okay? Or it changes color. So it's all values, it's all noise, it's all interchangeable. Your imagination, your creativity is the limit. You just need to bend the rules. And as we move forward, here we have some more materials that starts to be very, very hard to work with, but nevertheless, we need to cover them. So first of all, we have glass. Okay, and look at that. This is as simple as it gets. This is the most basic glass setup that you can have in Blender. This is a glass BSDF, which is also included in the principled shader, but this is sort of like the single unit, okay? Now, because glass has, the property of basically being hit by light and then absorbing some, reflecting some, and refracting some, and then that light gets scattered all around. This, in all softwares, is one of the most difficult materials to render out in a way that feels right. In fact, sometimes it doesn't even boil down to how the material is set up, but more how the scene, the lighting, and the geometry itself is actually set up. And so glass is super complex because you don't just need to nail the material, but you also need to nail everything else. The environment needs to be perfect, the lighting needs to be perfect, the 3D model needs to be perfect. Everything needs to align perfectly for you to get a good result. Right now, what we have here in terms of environments is a HDRI that is the Chiara sunset, and that HDRI has been also lowered to a sort of like dimmed down value. And then we have a sunlight that is creating our main illumination. And so what we have here is some glass that has a sort of mid value, and it ends up looking quite dark, which checks out because we are in a situation where there is not too much illumination going on, and we can kind of see through it, And as you might notice, this is also very noisy. It is noisy because we are right now previewing it sort of real time. And to render out glass, it takes a lot of time. So whenever you have glass materials, the calculations to figure out where light ends up going are much harder than compared to, say, wood, which is solid. And so it takes much more effort, much more computing power to figure that out. And therefore, the computer, like right now we're giving it the same amount of time to figure out glass as we're giving it time to figure out wood. And, whenever I move, it sort of refreshes. And so if you see, as soon as I settle my view, it solves the wood way faster than it solves the glass, and then eventually stops because I have put in a limit to it. And the way you do it is by going over render max samples. So right now it's to 4096, which is pretty high. It's pretty high, okay? This is a machine that can kind of handle it, but I do not want anything more than that. You might also notice that I have my denoise turned off. I keep it turned off because the denoise, what it does is that, it denoises, but we're working with noise. We're working really hard to create that noise. And so if I click this, it just messes things for me. It just destroys completely all the hard work that I put in. And yes, it does a decent job, at removing the noise, but with it, it's taking away too much stuff. So what I'd rather do is render without the denoise, which by itself also takes its own toll on computation, and then approach the problem of noise in other ways, but we'll see that over in compositing. Right now, we are talking about glass, and so to give you an example, here we have a very, very simple shader setup. There's a glass, there's the material output. That's as simple as that, which is, again, an abstraction of reality. This is not truly behaving like glass would. And so if you remember, and we need to go back a little bit to physics right now, light travels in wavelengths, and each frequency corresponds to different perceived colors. When the white light hits an object and then gets scattered and refracted, what happens is that it sort of gets split into individual colors. You might remember the iconic cover of the Pink Floyd album where there is a prism and a white light coming through it, and then the rainbow comes through, right? So that is exactly what happens. And so if you want to have, at the cost of much more higher computational costs, a more precise glass setup, this is it. I have it right here for you. And so what is happening over here is that we are splitting the refraction and reflection through a Fresnel, which is that node that we reviewed just earlier that creates a mask that changes based on our point of view. And then we're using that through the logic gate to split between refraction and reflection. We have here a value that I brought in and I have renamed with F2, or you can go over here, rename, but you should use F2 probably. And I have created a single value so I can control the roughness of both at the same time so they stay in sync. And then what is happening here is some magic with the index of refraction. So as light goes through an object, different frequencies get bent at different angles. So to create that in a realistic way, I have this setup which basically recreates the frequencies of the visible spectrum and sort of manipulates the degree at which they curve through an object. And this is known as dispersion, and it is also known as chromatic aberration. And what you can see is that as light comes through, around the edges, the light is broken, and we end up with this sort of aura where the red light comes through, and then the green light, and then eventually the blue light, which is the one that gets bent at the widest angle. So this is as deep as we are going to go into the physics of glass and light. I don't mean to give you another lecture on physics, but just so you know, it is possible to truly recreate complex physical behaviors. This is not even, a fully, physical simulation. This is still, to some level, an abstraction of it, although it provides a more realistic result. And so here there is another lesson that as a professional, you need to make choices of what is important, what is possible, right? So you might have a project where it is absolutely crucial that you have an accurate simulation of the behavior of light through glass. And then you need to make a plan for you to create this material, set it up, and render it. And this will take a long time, a really, really long time, because it's a very complex calculation. Or you might have another situation where you're tasked to do some rendering of some object that has glass, but you don't have too much time, or maybe the object is not the subject, maybe it's in the background, or maybe it's just, some scene that is a minor scene, and you don't need to spend that much time and energies on it, and then you can go about it with simpler materials. The lesson here is that you can go as complex or simple as you want. The answer to that depends on the requirement of the project. Just because you can do it, it doesn't mean that every time you need to do it. And just because you can go, down to the atom with every material, it doesn't mean that every material in the scene needs to have this depth of, realism. Now, before we move forward, I'm going to bring in a point light, which is a light that emits the same kind of light in all directions. In fact, in other softwares is also known as an omnidirectional light or an omni light. And right now you'll see that this material is interacting quite beautifully with this light that is trapped inside of it. Gorgeous. This is happening because on top of our surface material, we have a principal volume that is plugged into the volume socket. Now, if I move my light into the other glass shader, you will see that it sort of disappears, nothing happens, and that is because we do not have any volume happening over here. So once again, just another demonstration of how in-depth you can go with the development of materials and procedural shaders. As you can probably imagine, calculating the volume of an object is harder than calculating just its surface, because the behavior of the light becomes more complex, right? So once again, what I just said is that as a professional, you will need to make choices about what is needed and when. Moving forward, we have a very similar looking material, which is water. Now, water never comes in this shape, and so obviously it looks very, very odd right now. However, what we need to see over here is that we have a very similar setup to the glass. In terms of behavior, it is pretty similar. The difference is that the index of refraction is 1.333. This is one of those magic numbers that you will just commit to memory, and you will forever know that the index of refraction of water is 1.33. It's just one of those things that sticks with you. And the major thing that we have right here that we need to review is that we have a noise textures. So the noise textures is passed into the bump, which is creating sort of like a simulation of the waves effect. And if this was, rendered out, we would have waves move, right? So right now it's too hard to see because every time we go about it, it needs to recalculate it. So maybe you can just catch a glimpse. Let's see if I can do it with the denoise. So maybe you can just catch a glimpse of it, sort of like going through it. What we have here is a 4-dimension noise. What does that mean? Well, noise regularly comes into 3 dimensions, right? X, Y, and Z. When we need something to happen across time, then we introduce the 4th dimension of time, which is expressed by W. Now, W can be animated, like any of these values can be animated. You could hover over it and press I, and it would turn yellow, just like we have seen in precedence when we animated the rotation value and had an object spin around, right? Same exact thing. All of these boxes can be animated with very, very few exceptions here in the properties panel. But one alternative to keyframe animation, which is what you are doing with I when you are inserting a keyframe, is creating a driver. Now, a driver is the same concept, although it is kind of more advanced in the sense that you have to type in some specific things, and that will tie that value to something else. Let me demonstrate, which is far easier to show than tell. So I'm going to click on this and then create the hashtag symbol. So the hashtag symbol is what opens a driver. And then I'm going to type in frame. And what this will do is that it will create a driver which ends up being of this color, this sort of like purple violet thing. Tells me that there is a driver set up over here. And right now we are at frame 1, and so the value over here is 1. If I were to move to frame 60, this would move to frame 60. So right now the driver, what it is doing is syncing this value that I have set up as if it was a keyframe with something else. Right now we have determined that this driver should look at frames, but it could be anything else. Not only you can do that, but because frame is a placeholder for this value, what I can do is say divided 10, and now we have fundamentally a formula in here that takes the frame, divides it by 10, and so at frame 60 I will have value 6 over here. what this creates as a result is that we can then render our animation knowing that this value, which is the value of time, will change according to the frames, which again is something that is also tied to time, right? And so by setting this thing up this way, we have some water that will come alive when we render it out. Now, if this is not obvious, this does not pertain to water specifically, but it's something that you can set up for any property. I could have the hue change based on the frames, and every frame something changes hue, or it could be some other properties. But drivers are kind of advanced, and so what we will do is leave it at that. This is the number one driver that you need to know how to use, and it's probably sufficient for the moment being. And we are now moving on to some other materials that are just as complex as the one we have reviewed so far. So right here we have some jade. This is absolutely beautiful. I love it. It came out so well. So why jade? The jade has to it some very interesting material properties where it has that kind of like translucency to it, right? That lets some light come through, and what it does is that it ends up creating that effect that when you look it against the light, you have this, that it kind of looks brighter because you can see the light shine through it, right? The way this effect is achieved is through something known as subsurface scattering, also known as SSS. So the subsurface scattering lives right here in the principle BSDF under subsurface, and it does what it says. It controls the behavior of what is happening underneath the surface. This is just like glass, another one of those things that because it relates to a super complex behavior and interaction between light and matter, it's really hard to set it up in a way that just looks right. In fact, you will have to tweak those settings every single time. It's not a drag and drop solution as easy as dropping in a metal or a wood could be, because this has to deal again with the environment and the light and the geometry of the object. So that is why these are very complex materials, because there are more things, there are more parts to the picture that need to align just right. Now, once again, I will have to cite the famous lesson 16, where I explain to you everything you need to know about light and human biology and vision to sort of bring you to understand the subsurface. So what is called radius over here, it's basically telling us how much of that light is passing through the object fundamentally. That is a good way to think about it, that although might not be a good technical definition, is a good way to think about it to understand it. If you look at these three values, you should guess that they are RGB values, because we have a purple icon here that tells us that we are dealing with vectors. And so you can guess, just like if this was a color, that by having the green channel higher, this is leaning towards green. But because also the other numbers are not too far behind, this is a color that leans towards green, but is very close to white, which is creating this kind of like effect that echoes the green color of the material. If this was a red material, what I would have done is I would have set up as this predominantly on red, and now you can see that most of the light that is coming through is red. Now that I look at it, I'm thinking, well, this could be an excellent way to set up some precious gemstones like opal. That would be just awesome. However, right here we're dealing with jade, which has this very fresh green light passing through it. What else do we need to know about subsurface scattering is the weight. This is just how much is it taking effect. 1 is yes, 0 is no. And as you can see, it helps sell the material so much. And then we have scale. Scale, of course, relates to the object itself and how much the rays of light coming through are affected by this phenomena. And so the smaller it is, the less we're going to see this effect. So right now it's still there, but we're not seeing it as much. Whereas if I went overboard, things would start to break. As you can see now, it doesn't make any sense at all anymore. And so you want to always have values that make sense for the context you're working into. And lastly, we have anisotropy, which we have already covered in metals as a concept. And what it does here is, for all intents and purposes, sort of like affect the way in which light reaches you. And if we have a sort of in-between value, right? We are between this absolute anisotropy where all that green is coming back to us and a situation where things are just getting scattered all over the place. And for this material specifically, a good value would be 0.8, where most of that green is coming back to us and it is creating this very rewarding look. And we can see the same effect over here at the edges that really helps sell this material. And since I'm loving this material so much, I can foreshadow that we will look at it again in the future, because this is not as far as you can push things. You can go even deeper and really create jaw-dropping materials that just leave the audience in awe. And I could already stare at this the entire day and just move around it and just contemplate it. But let me tell you, there's more that can be done. I haven't done it yet because, again, time, and because today we are covering an in-depth to materials, but there is only so much that can be learned in one go. So we will return to this once again to go even more in depth into the making of complex materials. Right now, this is plenty enough. And the reason why we started with Jade to introduce you to subsurface scattering is that we can finally get to skin. Skin is another one of those infamous materials that is so hard to make look good. And that is for so many reasons, including the fact that, of course, under the skin, there is a ton of things happening, and skin is not the same everywhere. Skin wrinkles and bends and stretches and has different parts depending on different areas of the body. And also, we're not talking just about human skin, but every other kind of skin that can be out there for animals or, imaginary creatures like, dragons also have skin. So the material is obviously, it's known to be hard to set up. What do we have here? In the random walk, which is the surface method, there is another option called random walk skin, which fundamentally alters the way in which the subsurface scattering is happening in a way that should be set up to perform well and actually better for skin. Depending on the setup, either one might work best, depends on what you're going after. And so once again, to drive the point home, subsurface scattering is that property of objects where the light comes through it. And in the case of skin, especially human skin, you can have an example of it if you shine, for example, the flashlight of your phone through your fingers. You will see that light travels a good amount through it, and your fingers become this kind of like red glowing thing, which is different from an emissive material because they're not emitting light of their own, but rather the light is coming through. And you can see that as I bring this value up, you can see more and more of this effect here. The ears are usually, because they're thinner, a good example of this effect to take place. We can also see it very well if we look at things from the bottom. We can see that because there is a big mass occluding light over here, it's not really coming through, but here where it is thinner, it's starting to have this really beautiful feeling of substance to it. It really feels fleshy, as if blood was flowing through it. To expose you to the hardships of setting up a good skin materials, which this is by no means a complete example, I'm going to show you one of the most common issues, which is that you will have areas of the texture that start to look odd. Like here, we start to have this bluish tints, which, if managed properly, could add greatly to the realism. There are definitely areas of the body where a bluish tint could help sell the look. However, in this case, it would be a little bit too much. It just looks wrong, other than the fact that right now we have, skin material applied everywhere. And so what I want to show to you is that the weight has its own socket, right? So it follows the same logics and principles of masks. And in fact, in characters, when you see more sophisticated characters, you will have also maps that sort of exclude the same principle, the surface happening, right? So where we have white, the subsurface is happening, and where we have black, the weight is 0, so it is not happening. In this case, I put in a simple ambient occlusion and color ramp that I borrowed from previous materials. But as you can see, this is not the correct solution to create a mask around the eyes where you ideally would want it. And so this problem is still happening, right? So ideally we would want to have some sort of masking over here that prevents this from happening or limits it in a way that works towards our goal. Now, differently from previous materials like the Jade, what we have here is a texture-based material. So what I'm going to do here is click right and split vertically and change this to image editor. And from here, when I select this one, we can take a look at the texture that we have in. So, to reiterate the most important concepts that we need to take home from this lecture is that materials exist because the material output receives information. And mostly this information comes through the surface, although we can plug in also volume and even displacement, which is a way to actually deform the geometry of a mesh, supposing that it is dense enough, using the same concept of black and white, where the middle level is 0.5, and as we go towards 0, the geometry sort of sinks in, and as we go up towards 1, the geometry gets elevated. However, that is more advanced, and right here, if I show you the wireframe, we really don't have that much geometry, although this is not exactly a low poly either. And right here, I have it plugged in just to show you how the setup would work, but I've kept it to a very minimal level, so we're not truly using it that much. But anyway, we'll talk about it later a little bit more. So we have the output that receives information from a BSDF. The most used is the principal one, but we can use any other BSDF, like a diffuse, a metallic, a glass, and so on. Every BSDF has values slider that have sockets. From the BSDF alone, you can tweak those values to affect the entire material as one. But if you plug in information that is in the form of fundamentally an image, you can then affect different areas of the object with different values. So some of it could be 0, some of it could be 1. And so what we have said so far is that the number one thing we need to understand is that everything is noise, everything is value, and so they fundamentally are interchangeable. Now, when we are not working with procedural materials, meaning that they're not generated procedurally through mathematical formulas, we are working with textures, which are by all means images. So images come in with size, and professional textures follow the power of 2 rule. So for example, you have 4K textures that are at 4096 squared pixels and so on, like the one we have here. And the textures come with their own pros and cons. The pros of an image texture are that they can be more computationally efficient as opposed to complex node tree based procedural shaders, because they pack all the information inside the image at the cost of not having infinite resolution. And the other advantage is that because they are pictures, they can capture also the sort of like complexities and imperfection of the real world without you having to recreate everything. So the real world out there has tons of imperfection. Every material has so many imperfections that are close to impossible to recreate in a procedural way, mostly because although it is possible in theory, it just takes so much effort. So the point where the procedural approach stops is when you sort of cross that threshold of believable. But then you stop. You don't go and, create a mask for every single speck of dust, right? But with textures, you can capture those. In fact, this material that we have here is not procedurally generated, but it is a very close capture that has been then procedurally edited, sure, but it is a close capture of human skin. And as I said, skin, comes in all shapes and forms and kind of wrinkles and different, density of pores and so on. But regardless, the image that we are looking at is a diffuse image, also known as albedo. And so right now I'm going to spend a few minutes telling you how to properly set up things so that later on I can tell you how we can break them. So a proper texture, a professional texture, comes in seamless, meaning you can repeat it across and tile it and it never creates, the effect of being interrupted. This one is one of those. Secondly, the color information that is contained by the diffuse image, which by convention ends up in _D for diffusion, and it can also be called sometimes albedo, but it always conveys the same information, and that is color without shadows. So we don't want any shadows in our textures because the shadows are reactive to the light, and so they are created in real time based on the position of the light. We don't want it baked into our textures. Now, the next one we are going to look at is _R, which is for roughness. And as you now know, this is for, the quality of the surface. And just like the procedural nodes that we created, in every other material, this is nothing but the same, situation where you have some values between 0 and 1, and they're telling it where it is rough and where it is smooth. And then we have the normal maps. Now, the normal maps are the most easily recognizable because they always have this bluish tint due to the fact that they are hacking sort of the paradigm of the 3 channels that we use for colors in RGB, and they use it to convey the information X, Y, Z. Now, because of this, one change that you need to do is that when you bring in your texture information, it's gonna default to an sRGB color space. However, with textures that are single channel, we want to change this to non-color, and the same goes for normal maps and any other map that is not the diffuse, because what this does is sort of interprets the information of the pixels and their range in a different way. And what we want is to have the full extent of those range for our roughness, normal, and any other map that is not the color. If you forget to do that, it will still work, but you would be using the map in a sort of improper way. Now, because this is using RGB to convey XYZ, before we plug it into the principal BSDF, we need to pass it through another node, which kind of tells Blender that this is coming in as RGB, but needs to be really XYZ. And this node also allows us to change the strength of it, which fundamentally is affecting the blue channel, which is the most predominant one, which is the one causing it the bluish tint, which is the elevation of how much this thing is sticking out, so to speak. And finally, we have the H, which stands for height, which is also known as displacement. And this is fundamentally the same concept as the normal map, except that this goes into grayscale because, like I was saying, suppose that you have a surface. That surface comes at a mid-level, which by standard is 0.5, which represents the perfect gray, right in the middle between the white and the black. And then we are using this information to push down some parts of the mesh. So where the texture is black, it will go down, it will sink. And where the texture is white, it will elevate, it will go up. The difference is that the normal map is something that is used to fake the behavior of light without actually deforming the mesh. Whereas the displacement actually displaces the geometry. But in order for you to do so, you need to have the real estate, the density in the mesh to do so in the first place. Additionally, in Blender, you have to make sure that with your material selected, in the properties panels, you find your settings, surface, and change the displacement from just bump only to actual displacement and bump. This is a cycle feature that fundamentally allows you to non-destructively edit the geometry and put in much more detail. This is used for really high density, realistic renders because, as you can imagine, this is fairly expensive. Although in other softwares, like for example, Unreal Engine, there are techniques in which this can be used effectively to just drive in some more change. In fact, to that note, I will point out that although this was a super in-depth lesson, there is way more that can be explored and done. There is so much more to material design, which brings me to the next industry sort of insight, and that is that so far we have been reviewing 3D modeling and the very basics of lighting and animation. And at each step, we have said that each one of those is a job of their own in the pipeline. Well, materials are just the same. So in the pipeline of the creative industry, you have material designers that do this. They create materials either through textures or procedural nodes. And then there are technical artists who are sort of like more knowledgeable on the, technical side of how the computer works, how the software works, how the physics in the real world works, and they combine all that knowledge to create the most complex things. And so those two are other jobs that exist in the industry, that exist in the pipeline. And of course, this is a good level of depth for anyone to have. But if you were to become a professional material designer, there is much more to it, many more layers of depth. And in fact, there are specific softwares that have way more operators that you can work with, if you can imagine it, than this. So you can go way more complex than this, like way more. Okay, so before we wrap this up, now that I've shown you that this is the proper way to set things up, I can finally drive my point one last time that everything is noise, everything is value. And so if you have an image like this one, suppose that you go on Google and there's a texture that you really like, but it is just a photo. It is not meant to be a texture. Maybe it doesn't tile, and most likely it doesn't come with the rest of the most important information, like the roughness or the normal. Well, that is okay in the sense that you can kind of bootstrap it, because now that you have the knowledge and the secrets of the universe, I can bring in a color ramp, plug that image in there. And now look at that. Now I have something that is not too far from this. And so all that I need to do here is calibrate my lightness based on how smooth or wet I want it. And then I don't need this anymore. And I can bootstrap everything from this one. And although it might not be perfect, although it might not have the same nuances of a professionally created roughness map, which is its own thing, by no means I'm telling you that you can avoid them. But if you don't have them, you can sort of fabricate what you need on the fly. Same things with the normal and the displacement and fundamentally everything else. If you don't have it, what you can do from this image now is create for yourself a bump that will take in a grayscale image into the height and create for you this normal. And now you have something to plug into the normal. And now I can go in and edit it a little bit so that it is right. And again, although it doesn't have the same richness of a true normal map, we still get to work with stuff that ends up looking fairly decent. And so this is why I keep stressing the concept that once you enter the mindset that anything is noise, that anything is value between 0 and 1, you can do anything. You have no limits. If you're missing textures, you can make them. If you don't have any single texture, you can start from noise and still create it. As long as you have access to one procedural noise, then you can make any known material to man if you're creative enough. Alright, so that wraps it up. This was by far the most ambitious lesson ever. We covered so much, but at the same time, we covered many times one concept, and that is that now you have the power to make any material known to man, anything that you can imagine, you can create it, you know how to. What it takes between here and mastering it is practicing, challenging yourself to enter in this sort of mentality, and you know that everything is created through noise. What you need to develop is the knowledge of how to manipulate that noise. So it always happens in the same way, by manipulating the vectors and those values that the noise come with. And over time, you develop an instinct of what operation is going to produce which result. And so it's all about getting out there and familiarizing with this way of working. The important thing is that you stay organized and tidy. That is why I had my layers labeled, for example. And the nodes are really not that many. Most often is a texture coordinate going to a mapping, going into a noise, going into a color ramp, going into some sort of logic operator that is a mix RGB or a mix shader, and eventually finding its way to a principled and an output. So that is all there is to it. And I'm really not reducing things when I'm saying that those are fundamentally all the tools that you need to use, and everything that makes the difference is the sort of suggestions that you give through the distortion of that noise, and mostly the colors and properties of its surface. That suggestion, that hint, is the push that you need to give to a brain to see in it a material. Because that's what we are doing. We're seeing in it a material because the reality is constructed. Cool. I'll wrap this up. I leave you telling you that there are more advanced features. For example, you can group nodes and have sort of inceptions layer that you can use to keep things even more organized. There are other more advanced nodes that allow you to do even more sophisticated manipulations. But as you can see, this is already of tremendous power, and I will share with you these materials so that you can look at them, you can play with them, you can edit them, and you can practice. Cool. I'll see you in the next video where we'll dive deep into the process of lighting.